My name is Masha Iitkinen, and I am presenting multi-agent variational occlusion inference using people as sensors. Occlusions can hide dynamic obstacles that may appear on our path. Here, a truck is stopped at an intersection with a green light. This behavior is an indicator of an occluded pedestrian. Humans can make such inferences from their observed surroundings. Robots should have similar occlusion reasoning capabilities. We propose a CVAE driver sensor model that captures multimodality in its discrete latent space. Our real-time capable occlusion inference algorithm handles multi-agent settings with multiple observed drivers using evidential theory. First, we learn the CVAE driver sensor model, a multimodal mapping from an observed driver trajectory SH to the occupancy grid map, or OGM, of the view ahead of the driver, MH. The CVAE encodes MH and SH into a discrete latent space Z, which is then decoded into an occupancy estimate MH hat. During inference, only the trajectory is encoded, and the multimodality is captured in the learned prior P of Z given SH. Second, inferences from multiple observed drivers are fused together in the occluded regions of the ego vehicle's OGM using evidential theory. Our algorithm runs at 56 Hz. We validate our pipeline on an unsignalized intersection in the interaction dataset. The data is captured from a bird's-eye view, providing us with ground truth occlusion information. We visualize the results of the CVAE model. For a deceleration maneuver, the two most likely inferred OGMs show occupied space ahead of the driver. These results match the ground truth, where a vehicle is crossing the path of the driver. In contrast, a constant speed trajectory does not provide sufficient information to discern occupied or free space ahead, as the driver may be in traffic or on an open road. The CVAE reflects this multimodality by outputting two OGMs with similar likelihoods, one occupied and one free. Consider the full occlusion inference pipeline. Ego vehicle 83 is waiting to turn right at the intersection. Vehicle 33 is blocking its view while waiting to turn left. Without occlusion inference, the ego has no knowledge of occluded vehicle 92. Since observed driver 33 is stopped, our algorithm infers occupied space ahead, which captures occluded vehicle 92. When driver 33 accelerates, our algorithm infers free space ahead of the driver, so the ego vehicle could start making its right turn. In this scenario, ego vehicle 108 is waiting at a left turn behind observed driver 106. Visible drivers 113, 102, and 116 are also stopped. Oncoming driver 112 is occluded. Occupied space is inferred near driver 112 due to the observed drivers being stopped. Since we incorporate multiple agreeing measurements from these drivers, the inferred occupancy is of higher certainty. Once driver 106 accelerates, free space is inferred. The ego vehicle may then proceed with their U-turn or left turn. Thus, we propose a driver sensor model that learns a multimodal mapping from observed behaviors to the environment. Our algorithm handles multiple observed drivers and runs in real time as shown on a complex real-world intersection.